Hello, my name is Helen George, and welcome to my video for Lab 5 for Physics 2212. So in this experiment, we are demonstrating our understanding of Faraday's law and magnetic fields. Our goal is to create an experiment that observes the motion of a bar magnet as it falls through an aluminum foil tube, as well as to create a computational model that simulates the same experiment under ideal conditions. And then a basic overview of results, we found that a bar magnet falls at a slower rate when dropped down a foil tube as compared to its motion in free fall. And then the time of falling in our computational model was determined to be about 0.64 seconds, and the time taken to fall in our experimental model was about 0.7 seconds. Some fundamental equations that we're going to be using is that the total EMF of a system is equal to the nanocoulomb electric field times the change in length. And then another way of saying this is that it's the negative integral of the magnetic flux with respect to time. And then another way of writing this is negative delta kilo symbol for flux over delta t right here. We also use the Biot-Savart law, which gives us the magnetic field for an object with charge q, motion v at a position r. And then these come in handy in our computational model. We use Newton's laws to calculate the sum of forces, the vector sum of forces acting upon an object at a given time, and then through equation manipulation, we are able to derive two additional equations that can update the speed and position of the object. So in our experiment, our system was a bar magnet, our surroundings were the metal foil tube, and initially the magnet was held at rest above the aluminum foil tube. So the process went as follows. The north and south ends of the magnet were determined using the magnetometer app on our phone. The bar magnet was held stationary above the aluminum tube and the recording was started. The bar was released and time was recorded as it traversed the tube, and then steps 2 and 3 were repeated for a total of 5 trials with data being recorded throughout. And then these data points were averaged to determine an average travel time. And so some general information that we got: the length of our tube was 0.29 meters, the width of foil used was 0.003 meters, the inner radius of the tube was 0.0125 meters, the mu value that we calculated in lab 3 was 1.28, sorry, and then the mass of our magnet was 0.0245 kilograms, and then the average time taken was about 0.7 seconds. An additional explanation of our experiment is that we used an aluminum foil because it's not magnetic, therefore it won't exert a force upon our bar magnet. If a ferrous tube were used, like iron or a similar metal, a magnetic force would be exerted, which would skew our results. And then our magnet was observed to slowly fall through the tube as opposed to dropping quickly like it does in free fall. And then here is the code for our glow script model. First, we use some initial constants like we talked about earlier. We also initialized it with the mass in our mu mag. We created the magnet in the code right here, and then we also created a function to calculate the dipole moment. And then here we're calculating the flux, and then for general, we know that flux is equal to the B field times n hat change in area right here, which is basically what we're doing right here. And then here we're talking about Newton's second and third law. We're calculating and summing the forces, and then we are updating the velocity and position down here. And so then here is this visualized. The simulation isn't running. You can see down here the bar at the bottom, and then you can additionally see the velocity versus time graph. You can see right here that our time taken was about 0.64 seconds. This is a little bit faster than the value that we calculated in the experiment, and this could likely be because in our actual experiment the bar came into contact with the tube, which exerted a small frictional force on the magnet by the tube, and then this force would oppose the object's motion downwards, which would cause it to slow down more. And then because we didn't account for this in the computational model, it could explain why it moved a bit quicker than in our actual experiment. So what if the resistivity of the conductor were reduced to as close as possible to 0, and then how would that dynamic affect the falling magnet? So we know that resistance is directly proportional to resistivity. So if the resistivity increases, the resistance also increases, and then we also know resistance to be inversely proportional with current. And so if the resistance increased, then we know that decreases, and the current would have to increase, which would then increase the time taken to fall through the tube. And then what if holes or slots would cut into the tube, and then how would this affect the ring current in our model? And so if we had a bunch of holes in our tube, then the current flowing through would have to also go through these holes, which would lead to a general decrease in current. And then the force, the magnetic force on an object is directly proportional to the current, and so a decrease in current would lead to a decrease in force. Thank you guys.